Okay, good morning, everyone. We are going to continue with our discussion on stellar evolution. And as you probably have learned, and I hope you have learned from the previous discussion, that when we talk of the stellar evolution, we are talking of a star's development, and that includes its birth up until its ultimate demise. Now, we are going to review some of the things that we discussed last time, and first thing that we have to review is your Hertzsprung-Russell diagram, with the fact that as you go from your left direction, right towards left, there is an increase in your temperature there. So it's not the conventional plotting of the x-axis nga na andan ninyo nga from left to right kay mag-increase ang value, but for the Hertzsprung-Russell from right to left, dito ang increasing nga temperature nimo. And also from your y-axis, from top to bottom, from bottom to top, as that increases along the y, your luminosity also increases. And along with the colors, the red is the coldest color and the hottest is the blue. And I want you to remember the discussion or the analogy that we gave on the blacksmith, na the first color that will appear sa imong metal when it's very hot, particularly on the blacksmith, it will tend to have the red color. So that is really a property of a material class, na ang color nga i-emit sa imong material is associated with its temperature. Nga na it starts with orange, and then kung painiton pa gid nimo tong black sa blacksmith nga metal, mo orange, maabot siya yellow, and ultimately maabot na siya sa white or blue. But then again, we can't really do that probably on the earth's surface, kay I think you can understand na ang atong temperature is very low also. Taas ra kayong requirement para mahimong blue gid ang color niya. And another thing, no, you have to remember is that these are important quantities that you need to understand. Luminosity is a function, or is affected on how large your stellar body is. That means the radius of the sphere, assuming that the stellar body is a spherical shaped body, and how hot. That means it's closely associated with the temperature of the stellar body. So ang luminosity ana ga-vary na niya. And of the two constants, R and T, makita nimo since T is raised to the power of 4, the temperature has a greater effect on the luminosity of a body than its size. Kay R squared lang man ang imong size. And also about the absolute magnitude, so this is merely a process of comparing the stars fairly and squarely. Okay, diba? Of course, they are varying in distances, as you can see in this illustrations here. You have star A, B, and C. They vary in distance and size as they are scattered in the night sky. It's not very good approximation to say that those stars appearing dim to us are small stars, where in fact they are just very far. So if we are trying to like quantify the brightness, kasi magnitude is just associated with the brightness of your star. And then if you want the absolute magnitude, what we are doing here, class, is simply we are like simulating the distance of the star. How would they appear to us, or how would they appear with their brightness if they were at a standard distance of 32.6 light years? So remember my analogy when I said that it's just like ranking the student's height by making them align. So in this case, we are ranking the star's brightness by aligning them at some distance 32.6 light years. But then, of course, we can't do that. We can't move them. So what we do is we simulate based from our existing data. And also about the apparent magnitude. So this is still magnitude, or this is still brightness. No, um, the apparent magnitude is basically how the star appeared to us, ang iyang brightness as it is viewed from the Earth. And probably, I'm hoping you can still remember that the more negative the value of your apparent magnitude, the more bright the star is, such that the plus 25, or at least in the interval 20 to 25 asteroid here, has an apparent magnitude of positive 25, and you can't see that by your naked eye because that's very dim already. Even your brightest quasar is already plus 10, because they appear very dim sa Earth because of the fact that they are also very far. And in terms of the spectral class, I would just like to iterate again that the spectral class has something to do with both the temperature and, of course, the color of the star. So the hotter spectral class of the star belongs to the spectral class O, and the coldest or relatively cold ones belong to the spectral class M. Now, I have also already introduced this to you last time that this is a better way of memorizing the spectral class in terms of order. So it's O, be a fine guy or girl, kiss me. So it's O stands for the hotter spectral class corresponding to the blue colors, and M corresponds to the colder spectral class corresponding also to the red colored stars. Now, in the Hertzsprung-Russell diagram you are seeing here, class, basically I'm just going to summarize the thing about luminosity. The luminosity again is on your y-axis. So unsa may nakita nimo dira. Now as your star grow in size, so your radius also increases, meaning nagkadako imong star, makita gyud nimo that most of the large stars are situated in the areas on your Hertzsprung-Russell diagram located in the topmost portion here. Naana sila dira sa taas because again we learned that the radius r is directly related to the luminosity of a star. And of course, by logic, those of smaller sub nga sizes sa imong star, meaning smaller radius sa imong spherical nga shape, will tend to assume the places nga gagmay sa luminosity, just like in these areas here. Okay, so I'm just gonna take that out. So, para di kayo siya hugaw. Okay. So now again, the force that keeps the star stabilized is what we call in physics as a hydrostatic equilibrium. And you have to note that we are not talking of a solid here, class. We are talking of an ionized gas or in a state of matter na plasma siya. So what keeps the star stable is the interplay of these two forces. So we have the force of gravity and the thermonuclear force. And whenever there is instability, that means to say more often, it's really whenever the force of gravity overcomes the thermonuclear force, that will correspond to some unstable na phases sa imong star's life. And you will see in the Hertzsprung-Russell diagram that whenever that happens, your star tends to move in a different na position sa imong Hertzsprung-Russell diagram. And that will be the focus of our discussion this morning. Now, what keeps, again, answering the question, what keeps the star in your balance or to remain stable is the balance of your thermonuclear force, which is a byproduct of the nuclear fusion that is occurring on its core, and the gravity that is trying to compress the star because of its mass. So as you can see here illustrated in red, the lines are the representation of the force of gravity that is trying to compress the mass, the very large mass sa imong star. And of course, if that is happening, eventually dapat makompress na siya, magamay siya gayo. But then again, we also have some nuclear fusion processes occurring at the core that eventually balance the force of gravity. So as I've said, as long as these two forces are balanced, we call the star to be in a hydrostatic equilibrium, and the star is stable in that case. And here, as you can see also, this is just telling us that one of the key factor in the development and death of a star is really its mass. As you can see, the more massive, focus your attention on the top portion here. The more massive your star is, the faster is its the faster is its death. So mas less massive, dugay kay na siya class mamatay, kumbaga in layman's na pag-analogy na to sa life and death. Now, the focus of our discussion this morning will be on the low star development. But then again, these are some of the concepts that you have to learn, no? In the giant molecular cloud, there is actually the conservation of angular momentum present, or of course, it's bounded by the laws of physics. But what I'm just trying to say is in your giant molecular cloud, initially the masses are very spread out and it's being contracted by the force of gravity. It is initially spinning with an angular velocity of omega, gatuyok na siya class. But as the force of gravity compress it further and further, the masses will be concentrated towards a very small na area. So when that happens, the moment of inertia I will be reduced. So the resistance to resist change if the masses are concentrated in a very small area is very small. Therefore, you need a very small force lang to set that in rotation. So since there is a conserved na angular momentum in this case, the effect of that is thus the giant molecular cloud will have a very high angular momentum. Angular velocity omega. So it will be rotating very fast. So eventually then it will assume a spherical shape. Now, spherical shape, we already discussed this because of its geometry. So sphere has a minimum na moment of inertia of all of this. It has this moment of inertia here. And then when the moment of inertia is minimum class, the implication of that in physics is that it needs a very minimal force to set it to rotate. But pasabot, gamay lang kayo siya o force kinahanglan makatuyok na siya. Unlike sa dako og moment of inertia. So, when that is the case then, mao nang mas easier sa system na mutuyok siya, paspas gid siya magtuyok when it is assuming a spherical na geometry. Now, for this discussion this morning, this will be the focus of their discussion, as I've said, the low mass star development. So we only categorize the protostar na tong development or the star development into either low mass and high mass. So for this discussion, we will only focus on the low mass star development. Now, as you can see here, this summarize everything that you will learn about the low mass development. So you start from the nebula, or you could also think of this as where your giant molecular clouds are located within your nebula. And then after that, the generation of your protostar. So this is not yet a star. And then after that is the main sequence na age sa imong star. And by the way, I will just tell you ahead that this is the process where the star is fusing hydrogen into helium. And then after that, the star will become or will cross sa imo ang giant nga or red giant or red supergiant na mga phases niya, and this is because of the instability of your hydrostatic. Wala na to equilibrium kumbaga nga na meet mo nang mopadulong na po na siya red giant. And eventually the byproduct of that is the generation of your planetary nebula. So this is where the outer core, more like the outer layer of your stars are being shed. And then eventually, the ultimate demise of that is white dwarf. So this is just the remaining core sa imong star. Mao na lang na nabilin class because the rest, actually naa na diri ang planet imo ang kuan, white dwarf. The rest of the masses are actually like thrown into space. So the remaining core of the original star will just be the white dwarf. And eventually, as I've said, so the white dwarf will be what's this? Giving off energy, so it will become black dwarf. But since our universe is very young still, currently this does not exist. Wala pa tay experimental data suggesting asay location sa usa ka black dwarf. Because if that is the case, kung makakita mo black dwarf karon sa atong universe, then probably our models are wrong. Ano nakita ang black dwarf nga atong age sa universe Carter 13.6 billion years pa man. Okay, so mauna nga medyo dugay magugay na ma-develop imong black dwarf. So this is just again exemplifying the point that in science the hypothesis must be both testable and falsifiable. So kining black dwarf isa na siya ka example ana niya. Okay, so let's proceed now to the discussion on the protostar development. Now, as I've said in the previous discussion, I'm trying to make this very short for just like 30 minutes. So it's really the mass that is the key player class in the development or evolution of your star. Now, as you can see here, you started from a giant molecular cloud on this section of the illustration. And when the giant molecular cloud contract, of course, it will start to spin rapidly because it has a low moment of inertia, and eventually it will assume a spherical shape as you can see here. Pero class, if it's not really massive enough, it won't be a star at all, okay? Dili man enough ang force of gravity nga mo squeeze ana niya nga mo abot ang iyang temperature nga maka-fuse siya og hydrogen into helium. So dili gid na siya tanan pod mahimo nga star. So the failed star nimo karon kay ginatawag nimo na siya as your brown dwarf. So not all nga mahimong star from a prototype. So we have brown dwarf, so those are your failed stars. Now eventually, pero kung mas dako or sufficient ang mass nimo class, it will become hotter and brighter ang imong star. So nakita nimo diri nagsaka yung luminosity sa imong Hertzsprung-Russell as well as your temperature. Take note, this is the area of higher temperature. And then also, as it increases in luminosity class, it's being squeezed further by the force of gravity. So eventually, mubaba na po na iya ang luminosity. Anong mubaba yung luminosity? Take note, as it's being squeezed, ang iya ang size ana mo gamay sab kayo. So if kasugod kay ingon ani nga size, eventually mo assume siya smaller nga shape. It's because of the constant na squeezing sa imong force of gravity. Okay, so that's why the luminosity as it evolves mo decrease yung luminosity. I don't know why, but I can't draw a smaller circle maybe. Just like that one. So from that original shape, padulong siya sa mas gamay nga shape. So this also explained this part here, the one that I am highlighting. Na as your star progresses towards the main sequence, ang luminosity niya ni baba. Meaning nilihok siya paubos ba on the y-axis nimo. Kay ni gamay man sab siya size kay continual ang compression sa imo ang force of gravity. So continual ang compression sa imong force of gravity, makita nimo ni class akong alanan nag A o B. So this is point A here, just for clarity. This is point B. Although in point B, nigamay yung radius, no, nigamay yung luminosity, but the temperature at this case increases. Maunang nidagan ang imuhang star development on the Hertzsprung-Russell diagram towards the left nimo. Kay mosaka man ang temperature, kay murag ang compression sa force of gravity ba nagkakusog, mauna nga mosaka po na siya. Okay, so and then, as you can see there, moadto na din na siya sa main sequence. And I've said the main sequence is the stage where the star will be synthesizing hydrogen to helium. Okay, now, what if mag-start ka very massive sab kaayong a star? Or very massive ang dako na kayong mass sa imong star. So just like this one. So if it's too massive, it also becomes very unstable and hence the more like premature death ang mahitabo sa imong star class. Dili pud siya maka-form og main sequence or mahimo nga star. If that is the case, kay too much ra kayo ang force of gravity mo, collapse siya diretso. So dili na siya maka-fuse og hydrogen to helium. Okay, so nakita gyud nato aning example that thus the mass is really the key player in everything sa imong star's life. Okay, so also I would just like to tell you ahead that this is the evolution that will happen sa imong low mass stars. So syempre once it's already in the main sequence, so it's fusing hydrogen to helium, there will be instances class nga agian sa imong star. For example, it will go towards the red giant. After mag-red giant, meaning musaka yung luminosity and magka-bright siya gaayo, kamo dako man iyang size, dako ang radius r sa imong sphere ba. After that one is it will, pero nigama yung temperature na notice mo ni padulong siya sa right, so the temperature on the x-axis there decreases. So although ni saka yung luminosity, nigama yung temperature. Dayon musaka na po na siya diri. Once it burns helium, mo cross na siya aning a path. We'll just find a better color. Mo cross na siya aning a path, so there will be an increase in the temperature kay nag-fuse ng helium. Pagkahuman na niya, pero ang iyang luminosity is a little bit decreasing. Dili siya nagka-bright og ayo. And then after that, once nag-initiate na mong helium burning class, muswell na po na siya or possibly muswell na po na iyang size, musaka na siya. So associated with the increase in the radius or the size is of course the increase in the luminosity. So saka na po na siya dito dayon iyang temperature mo baba sab. So na-notice nimo every time your star actually expands in volume, mo decrease ang imong temperature. Mao nang mopadulong siya sa imo ang right hand side sa imong x-axis sa Hertzsprung-Russell diagram. And eventually for low mass star, it will evolve into a planetary nebula na medyo luminous nga body, taman sa muadto na siya sa iyang ultimate nga fate, which is a white dwarf. So this summarizes the development that will happen sa imuhang low mass nga star development. So we will talk about the processes that led to this development in the preceding sections.